Hello everybody. I'm going to talk about blocking violations in reactive programming today. My name is Felix Dobslaw. I'm a computer science assistant professor at Mitigations University. This paper is based on a bachelor thesis produced by Vallin and Sundström. I'm going to introduce briefly what reactive programming is, what blocking violations are, and the role of schedulers. Then I will present the study and eventually conclude the work with an outlook on future work. Two things to note about reactive programming. It's a declarative programming paradigm, which means that it's focusing on describing what you want to achieve with the code, except as opposed to how you want to achieve it. And it's focusing on data streams. So instead of focusing on static data structures as an object-oriented programming, for instance, we're looking at more dynamic data structures. Microsoft Research has played an important role in producing some of the libraries. The RxJava library was created there starting 2007. I'm not aware of different streams. It'd be interesting if somebody can tell me more about that. The general objectives, at least some of them, are simplification on top of existing high-level languages in terms of concurrency, error handling, and the composition of events coming in from different data sources and being sent to different data sources. Some may consider the observer pattern done right. Usually it comes as an extension to existing languages such as Java and C#. And it's very commonly used for mobile development, for instance, in Android, also for web service development, distributed systems. And in this study, we're specifically looking at Java and the implementations based on ReactiveX, which is RxJava in Project Reactor. So as an example, how would we execute a program procedurally? We would have a data structure that we retrieve, call the test results here, for instance, and we would loop through them in order to send notices to all the subjects about the outcome. And in case in case it's a positive test, we would add them to some secret database, say. This is a very common way of describing it. And procedural code is eagerly executed, meaning that it's going from the top down, line by line. And we don't know really whether send notice and add to secret database are executed synchronously or asynchronously, meaning that we're waiting for the result or not, because that is a semantic that is hidden here. In RxJava, the same code would look something like this, where we would retrieve a data structure. In this case, it's not a static data structure, it's more of a dynamic data structure that handles a side effect here on the do on next with sending the notice, does some filtering, maps, and then eventually, when subscribing, it activates the code, the entire code stream. So as opposed to the procedural style above, this only gets activated once we call the subscribe method, and then it's started. So there's a lazy evaluation involved. And we also speak of code being blocked if it's synchronously executed, so the thread is being blocked, and non-blocking if it's asynchronously executed. So now, what is a blocking violation? We can look at this code, and we don't know really if the consuming code here, we have two examples of consuming code, the side effect and the actual consumer code. If they're blocking, we don't know. But the recommendation for reactive programming is that we don't do any blocking in terms of I/O and so on, because that could halt the execution for multiple processes. An example of actively blocking is the thread sleep, and this can not only be forbidden but lead to problems. And here I'm going to explain what the problem is. I'm sure you're all aware of thread pools. Threads are a scarce resource, so we want to pool them in order to reuse them. And if we have some tasks coming in, say this is a thread pool with 2 threads, if they are long running, then 2 of them will actually block the resources, and the third one is starving. Now in reactive programming, this is by design reduce the risk of doing that, or at least at a finite granularity level. It's possible for you to create more responsive applications, because we are separating things into dispatching, the actual service, the service, and then the reaction. So only the dispatch is being placed on the initial schedule, and then it is actually 1A is deciding that this can be scheduled. The long-running task that is actually blocking can be scheduled on another thread pool, and in the meantime, 2 and 3 can be executed because they are following the same kind of principle. They should also be fastly executed, and at some point then we can, once 1B is done, assign one C to the thread pool, which is the reaction to what's been consumed. So by creating an abstraction that is called the scheduler, in reactive programming, we are abstracting away the management of the thread pools, and we can really per line or side effect and consumption code decide on what kind of thread pool is run. And so probably we would assign a non-blocking sign on the main loop of the application here, and a blocking sign on the, say, I/O operations, because we might have many operations with a lot of hardware or other distributed components, and there we might have to wait. And so these thread pools might have very different properties. Like the non-blocking one might have a fixed amount of threads, whereas the blocking one might be more elastic. So now to the research questions that we are addressing in this work. We just want to know how prevalent the problem of blocking violations is in open source projects, and if we could find out the main causes for not correctly executing and blocking in non-blocking schedulers, which you can assign the schedulers to be non-blocking, and what suggestions can be made to fix the blocking violations. In general, there is a lot of work being done on concurrency issues. Concurrency issues are hard to trace down and hard to reproduce, and therefore also hard to test. And we have both failures and faults that have been highly investigated, and we have references about that in the paper. Some work that's been done by Mamun in 2011, 2010. They executed different concurrency failure tools in order to find failures, and they detect actually that each tool, different tools, detected about 25 problems in about 25% of the projects, and different problems in the different projects. So there are many concurrency issues out in open source, and there is a list of other references that we've been placing in the work. So concurrency problems are a real issue, and blocking violations is one of the issues that hasn't been investigated so far. So our approach is to first identify a tool to detect the blocking violations, and block count is one of these tools that allows us to do that on the bytecode level. And then the second step was to shortlist a certain number of projects so that we could instrument those projects and run them locally on a test environment. And we shortlisted 60 projects based on certain criteria such as star ratings, FOX, and that they should have a certain size of a testing suite so that we can cross-relate that to code coverage. We set them up locally. We could do that with 29 of those because we had some issues with the others in terms of compilation and other errors. Then we instrumented them with block count. What we did on top of that was that we added what we call here a reference violation to each of the test classes, so that we made sure each of them is really run with block count activated. So we were expecting to find at least one violation, and the violation here is raised because we're doing a thread sleep in what is to be expected to be a non-blocking thread pool in the scheduler. Eventually, we were collecting the statistics per project, trying to find the root causes in 6 year, and maybe the most important part, to identify mitigation strategies for the root causes and implement them. What we found was that 7 out of the 29 contained 190 violations. And this is a bit funny because this is 24%, and so roughly 25% as re-identified in this study. There are many many projects that have concurrency errors. And what we find here is that in terms of false negatives, we could say that we have a coverage of approximately 60%. So yes, we don't really measure the whole magnitude of the problem, but we get a good idea of it based on our findings. It wasn't the objective to check out the magnitude, but just capturing a signal if there is a problem. And I think we kind of found that here. We also cross-related to the other 22 projects, which we didn't find violations in, and we could only find a slight difference in coverage. And so statistically, it's too few entries here to make a real statistical test. But yeah, in terms of false positives, we were actually trying to make sure, because some of these projects are from the same organization that's creating the block count tool, to find out if there are some calls that are actually intentional, and there is in Blockhound a way to customize and make sure that certain um, blockings are not considered a violation, and we made sure in our tests that this was activated for each individual project that defined them. So we should actually capture the signal quite well here, while we didn't contact the original programmers yet. I think that's an interesting route for future work. We could identify 5 root causes, and yeah, they're listed here. We have basically I/O operations being the main problem, then sleep, actively sleeping, and the park operation, which is interesting, makes 18% approximately. And the park operation is interesting because this is what actually could lead to a deadlock, because we're actively waiting for a resource to be obtained, a blocked resource. And an interesting insight is also that none of the project actually has more than two different root causes that could be found. And we found 2 mitigations, or there are basically 2 mitigations that we could come up with. Not surprisingly, we could try to turn a blocking call into a non-blocking call. Not always easy, because that's a general problem of moving between regular imperative code and reactive code. And because you're expecting some outcome, and so it's kind of a mismatch of the both paradigms. The other alternative that worked pretty well was to schedule things on the non-blocking scheduler. And here are 2 examples of that we also present in the paper. You see here that there is a wait, and so a latch is actively waiting for something to be unlocking. And instead of scheduling this on the single scheduler, which you do by the subscribe on call here in the operations, we move that to the elastic scheduler. So this kind of relieved a blocking scheduler. And another approach then is to wrap code that is on the consumer side by a component that actually is able to assign this to a scheduler that allows blocking operations. Here's the block operation. So in conclusion, blocking violations are a tangible issue. So 24% of the projects had them, and we made sure that the projects at least are used in our studies. We identified 5 root causes, 2 ways of mitigating those, and out of those 190 problems, we could actually make them all run and have the tests pass, which was nice. For future work, we got to look into false negatives. We had those 40% of code that we didn't cover. And what did we get wrong possibly? We have to get back in touch maybe with the developers and see what their take is on those violations that we found. What is the real impact of those in terms of performance, but also concurrency failures such as deadlocks should be investigated more deeper. And if there is a possibility to have some pre-compiler support for this so that it simplifies for the developer at development time, what would be really great would be support for Android, so that Blockhound is currently not possible to work on Android, but that would be really neat because there is a lot of code, and that would give us better coverage of the open source community use of reactive programming. So thanks for your attention, and with respect to the provoking questions, in general, should we look into something more deeply with respect to reactive programming? That's one of the questions, but more specifically, is covering blocking violations enough? Look at this piece of code. We have a while loop here, which is clearly not blocking, but it actually doesn't return. So are we spending more time on the right problem, or should we address this problem more broadly? Thank you very much.